Okay, so quantum physics can seem a little intimidating at first,
Oh,
right?
absolutely. It's definitely got a reputation for being mind-bending.
But honestly, it's super fascinating stuff. And once you get past that initial, what is going on here, feeling, it's really quite amazing.
I completely agree. There's so much to explore, and it really challenges how we think about the world.
Exactly. And today we're going to focus on a concept called observables.
Ah, yes, observables. These are essentially the things we can actually measure in the quantum world.
Right. Like, think about an electron. We might want to know its position or its momentum. Those are examples of observables.
Yeah, good examples. And what's really wild about quantum physics is that the act of observing something actually changes the thing being observed.
Hmm.
It's not like that in our everyday experience.
Not at all. In our normal classical world, we assume things have definite properties,
Yeah.
whether we're looking at them or not. Like,
Yeah.
my coffee mug is right here on the table, even if I close my eyes.
Right. But in the quantum world, things are much fuzzier. Those properties, like position or momentum, only become definite when we measure them.
It's like the act of measuring forces the quantum system to make a choice, you know?
Yeah, it's a great way to think about it. Like, imagine a spinning coin. Before it lands, it's potentially both heads and tails.
Yeah, it's in this weird in-between state.
Exactly. But the moment you look at it, bam, it's either heads or tails. It's like
Yeah.
the coin decided what to be when you observed it. And that's very similar to what happens with particles in the quantum world.
So in that sense, it's almost like the act of observing is what creates reality.
Well, that's a pretty deep philosophical question, actually. But the analogy with the coin does help illustrate how measurement plays a different role in quantum physics compared to classical physics.
Let's bring it back to our electron example. In classical physics, it'd be like a tiny marble with a fixed position. But in quantum physics, it's more like a hazy cloud of possibilities until we try to measure its location.
Yeah, a hazy cloud. I like that image. It captures the idea that the electron doesn't have a definite position until we measure it.
And it's that act of measurement that
Mm.
forces the cloud to collapse, so to speak, and the electron chooses a specific spot.
Right. And this is where the concept of operators comes in. In quantum mechanics, each observable, like position or momentum, has a corresponding mathematical operator. It's like a tool, you could say.
A tool for making a specific measurement.
Exactly. And these operators act on the system's quantum state, which is kind of a mathematical description of the system's current condition.
Okay, so it's like a set of instructions that tells us how to measure a particular property of the system.
Precisely. Now, when an operator acts on a quantum state, it can produce certain special states, which we call eigenstates.
Eigenstates, right.
Yeah.
Remember, those are connected to the possible outcomes of our measurement. Yeah.
You got it. Each eigenstate has a corresponding eigenvalue, which is the specific value we would actually get if we measured the system in that state.
So if we measure the energy of a system and it's in an energy eigenstate, we'll get a specific energy value, an eigenvalue, as our result.
Precisely. It all ties together beautifully.
But here's the thing. We've talked about how quantum systems can exist in superpositions of multiple states at once. That's like the whole being in multiple places at the same time idea that people often associate with quantum physics.
Oh, yes, the famous superposition principle. It's one of the cornerstones of quantum mechanics.
So does that mean a system can also be in a superposition of multiple eigenstates?
Absolutely. It's not limited to just position or momentum. It can apply to any observable. It's like our spinning coin again. Before we look at it, it's a blend of both heads and tails. Similarly, a quantum system can be in this mixed state of multiple eigenstates.
And then, bam, when we measure it, it collapses into one of those eigenstates.
Right. And the specific eigenstate it collapses into is determined by probability. The coefficients in that superposition essentially tell us the likelihood of each possible outcome. We can calculate those probabilities, but we can't predict with certainty which eigenstate it will choose.
So there's always this element of randomness baked into quantum measurement.
Exactly. And that's one of the things that makes quantum mechanics so fascinating and sometimes frustrating to study. It challenges our classical intuitions about how the world works.
It definitely makes you rethink the nature of reality. So we've covered a lot of ground here, but I think we're ready to dive deeper into the measurement problem itself. Because the idea that simply observing a quantum system causes it to choose one outcome out of many possibilities, that's where things get really mind-boggling.
You're telling me. And that's precisely where these different interpretations of quantum mechanics come in. They're attempts to explain what's really happening during this collapse of the wave function. It's a wild ride, so buckle up. So we've kind of been tiptoeing around this idea, that measurement really changes things in the quantum world, right? It's one of the biggest mysteries, I think, and has led to some pretty wild explanations.
Yeah, no kidding. I'm ready to go down that rabbit hole. But before we get too deep into those interpretations, can we maybe just take a step back and really make sure we get these Hermitian operators you mentioned earlier?
Yeah,
They seem pretty crucial to this whole measurement puzzle.
absolutely spot on. They're key players in all of this. So remember how we talked about each observable, right? Like position or momentum or energy or spin. Each of those has a matching Hermitian operator. They're like the mathematical tools we use to figure out what we might get when we measure something.
Okay. And those possible measurement results are the eigenvalues tied to each operator, right?
You got it. And what makes these Hermitian operators so special is that their eigenvalues are always real numbers.
Makes sense. After all, we can only measure things in the real world, right? Can't really observe something with an imaginary value.
Precisely. Those real eigenvalues from Hermitian operators are how we connect that abstract math of quantum mechanics to actual measurements.
All right, so let's say we've got a quantum system and we know its wave function. What happens when we apply a Hermitian operator to it?
Okay, so when a Hermitian operator acts on a wave function, right, it can produce a bunch of special states, and we call these eigenstates. Think of them like the possible states that are allowed for that specific observable we're looking at.
So like if we're measuring energy, the eigenstates would be the specific energy levels the system could have.
Exactly. Each eigenstate has a corresponding eigenvalue. That's the specific value we'd actually measure if we found the system in that state.
Okay, that makes sense. But we've also talked about how quantum systems can be in those superpositions, right? Like
Yeah.
multiple states at the same time. So can they be in a superposition of multiple eigenstates as well?
Oh, absolutely. That's where it gets even more interesting. It's like our spinning coin again.
Yeah.
Before you look, it's potentially heads, and tails at the same time. Similarly, a quantum system can exist in this blend of different eigenstates all at once.
But when we measure it, bam, it collapses into just one of those eigenstates.
Yeah.
And which one it picks is determined by probability.
Right. You nailed it. The coefficients in that superposition basically tell us how likely each outcome is. We can calculate those probabilities, but we can't know for sure which eigenstate it'll choose.
Feels like we're always dealing with this inherent uncertainty in quantum mechanics. We can know the possibilities, but never the exact outcome. Kind of reminds me of how we were talking about those different representations of quantum states. It's like looking at the same thing, but from different angles.
You're exactly right. Different representations give us different tools to analyze the same system. Like if we're interested in a particle's position, we might use the position representation. The wave function there gives us the probability of finding that particle at different spots in space.
So it's like a probability map of where the particle might be.
Precisely. But if we want to know about the particle's momentum, we switch to the momentum representation. It's a different way of looking at the same quantum state, but it tells us about the probabilities of the particle having different momenta.
So it's not that the particle has a definite position, A and D, a definite momentum at the same time. It's more about which aspect we're choosing to focus on.
That's a really good way to put it. It shows how position and momentum are kind of intertwined in quantum mechanics. The better we know one, the less we can know about the other. That's Heisenberg's uncertainty principle in action.
Okay, I think those representations are starting to click a bit more. Maybe we could look at a specific example to solidify. We talked about spin before. How does that work with these different representations?
Spin is a great example. Remember, it's that intrinsic property of particles like electrons. It's like an inherent angular momentum, but not spinning in the way we normally think about it.
Yeah, it's one of those don't try to picture it too literally things in quantum mechanics.
Exactly. And spin is quantized. It can only take on specific discrete values. For electrons, it's plus or minus 1/2.
Like a switch that can be either up or down, no in between.
Perfect analogy. And we use the spin operator to analyze it, another one of those Hermitian operators. It acts on the particle's spin state, and its eigenvalues are those plus and minus 1/2 values that we can actually measure.
So when we measure an electron spin, we're basically asking it, are you in the spin-up state or the spin-down state?
Exactly. And by measuring it, we force the electron spin to collapse into one of those two eigenstates.
Here's what I find crazy, though.
Hmm.
We can measure spin along any direction we want in space, right?
Right.
But the answer seems to depend on which direction we pick.
You're absolutely right. That's where things get really strange. Let's say we measure an electron spin along the z-axis and we find its spin up. If we immediately measure it again along the z-axis, we'll get the same answer, spin up.
Okay, so far so good. It's like once it's made its choice, it sticks with it.
But here's the twist. If we measured the spin along a different direction, like the x-axis, the outcome of that second measurement is totally random, 50-50 chance of spin up or spin down along the x-axis.
Hey, so measuring along one direction messes things up for other directions. It's like
Yeah.
the electron forgets what it chose before.
It's not about forgetting, really. It's more like measuring along one direction disturbs the spin state and makes it uncertain along other directions. Another example of how measurement isn't just passive observation in the quantum world.
Okay, I think I need a minute to process that. This quantum spin thing is wild. Seems like we can't know the spin along different directions with perfect certainty at the same time.
You've hit the nail on the head. It all goes back to Heisenberg's uncertainty principle. We can't know certain pairs of properties perfectly at the same time, like position and momentum or spin along different axes. The more we know about one, the less we can know about the other.
It's like this uncertainty is built into the very fabric of reality at the quantum level. It's amazing how much we've learned about this strange world, but also humbling how much more we don't know.
Couldn't agree more. And this all ties back to that fundamental question. What's really happening when we make a measurement in quantum mechanics? What causes that wave function collapse? These are the big questions that all these different interpretations are trying to answer.
Well, now I'm even more eager to explore those interpretations. Let's jump into that rabbit hole. Okay, let's dive into these interpretations then. We've talked about how measurement is this big deal in the quantum world, causing superpositions to collapse and all that. So what are some of the ways people try to explain what's really going on when we make a measurement?
Well, one of the most mind-blowing ones, and maybe the most famous, is the many worlds interpretation. It basically says that whenever we make a measurement, the universe splits into a bunch of parallel universes. Each universe represents a different outcome of that measurement.
So it's not that the wave function collapses and only one outcome becomes real, but rather all of the possible outcomes happen, just in separate branches of reality. Like there's a universe where I won the lottery last week, even though in this one, well, I definitely didn't.
Yeah, that's the general idea. The many worlds interpretation gets rid of that whole collapse issue by saying everything happens, just not all in the same universe. The wave function just keeps branching out into these parallel universes, representing all the different possibilities.
Wow, that is wild. It definitely solves the problem of one outcome being chosen over others.
Yeah.
But it also means there are countless versions of ourselves out there experiencing every possible scenario.
Kind of makes your head spin, doesn't it? It's a lot to wrap your head around, for sure. And it's not without its critics. For one thing, it's not clear how we could ever test if these parallel universes actually exist or how they might interact, if at all.
So what are some of the other interpretations out there that try to make sense of this measurement mystery?
Well, there's the Copenhagen interpretation, which is probably the most widely taught and used one. It's a bit more, I'd say, pragmatic. It focuses on what we can actually observe and measure without necessarily trying to explain the underlying reality too deeply.
So it's more about accepting the strangeness of quantum measurement and working with it, rather than getting into deep philosophical debates about what's really happening.
Yeah, that's a good way to put it. The Copenhagen interpretation really emphasizes the role of the observer in defining reality. It's almost like saying that the act of measurement forces the quantum system to pick a specific state, and that becomes our observed reality.
So it kind of avoids the issue of the wave function collapsing by saying that observation creates the reality we experience.
In a way, yeah. It focuses on the idea that different perspectives are complementary. Like, we can't know both the position and momentum of a particle perfectly at the same time. The better we measure one, the less we know about the other. And it's the act of measurement that determines which perspective we're taking, shaping the reality we observe.
Okay, so we've got two very different takes on quantum measurement here. Are there any other big players in this interpretation game?
Oh, there are a bunch of other interpretations out there, each with their own strengths and weaknesses. Like there's the de Broglie-Bohm theory, sometimes called pilot wave theory, which proposes that there are these hidden variables that guide how quantum systems behave. And there's the consistent histories interpretation, which focuses on sequences of events rather than individual measurements. It's a whole philosophical playground out there.
It's pretty amazing how one fundamental thing in quantum mechanics, the act of measurement, can lead to so many different ways of thinking about reality itself. It really speaks to how deep and strange this subject is. So where does that leave us? Is there any way to know which interpretation is the right one?
That's the million-dollar question, isn't it? And to be honest, we might never have a definitive answer. Some people even argue that it's not the right question to ask. because a lot of times the different interpretations end up making the same predictions about the outcomes of experiments. It might come down to which philosophical framework clicks best for you. Which explanation helps you make sense of this weird and wonderful quantum world.
It's both fascinating and humbling. I mean, we've come so far in understanding how the quantum world works, but we're still grappling with what it all means, the fundamental nature of reality at that level.
Yeah.
And maybe that's okay. Maybe the journey of figuring it out is as important as finding the answers.
I totally agree. Quantum mechanics really forces us to question our intuition and just embrace the unknown. And who knows what amazing discoveries and even wilder interpretations are still out there waiting for us as we keep exploring. I'm excited to see where this all goes.
Me too. It's a good reminder that science isn't just about getting the answers, but about always asking questions, pushing those boundaries of what we know, and just being okay with the mysteries that make the universe so interesting in the first place.